This is an AQA GCSE Chemistry question and it's based on the atomic structure and bonding topics. So I'm going to recommend you try each section, pause, and then check the answers once you've gone through them. So here's A and B, Part C, Part D, Part E, Part F, and finally Part G, a 14-mark question in total. So going back to Part A, we've got the dot cross diagram. Now the first thing to think about here is that hydrogen has one electron in its outer shell. It wants two. So whenever you have hydrogen in a compound, it will always be one pair of electrons that we can see here. Each H has put one in and taken one back for sharing. To complete this, we need to recognise that nitrogen is in group 5 and realise that that means that nitrogen has 5 electrons in its outer shell. So we've used 3 of them in bonding pairs, so we've got 2 left. And then just as a very quick double check on this question, I can see that each hydrogen has got 2 electrons, a full outer shell, and nitrogen has got 8 electrons in its outer shell, also a full outer shell. In terms of the limitation, this is not a common question, but what we're looking for here is that the model does not fully describe the shape. It's actually a 3-dimensional structure, but the diagram shows it as 2-dimensional. Moving on to Part C, and we're asked why ammonia has a low boiling point. With any question on melting and boiling of different types of structures, and we might be talking about molecular covalent, giant covalent, ionic, metallic, we have got to use the right terminology. So when we look at this, first of all, we're deciding the bonding type, and it's a simple covalent or a molecular covalent compound. That means that when we boil it, we're overcoming intermolecular forces, and we have to recognise that they are always weak. Because they have weak intermolecular forces, not much energy is needed to overcome them. Moving on to Part D, and we've got ammonia reacting with oxygen in the presence of a metal oxide catalyst to produce nitrogen and water. Which of these is most likely to be a catalyst? Well, one of the things about catalysts that you have got to remember from this topic, and it comes later in year 11, is that transition metals are good catalysts. So we're finding something that contains a transition metal. Calcium is group 2, magnesium is group 2, sodium is group 1. Chromium is a transition metal. So the correct metal oxide is chromium oxide, Cr2O3. Moving on to Part E, and we've got quite a big calculation here. It's worth 3 marks. And you are working out the overall energy change. So we've got to consider that the breaking of bonds is endothermic. And I've put those calculations in here. We're breaking up 4 NH3s. That's 12 NH bonds, each of them 391 kilojoules per mole. And we're breaking 3 O double bond O bonds. That's 3 times 498, taking you to a total of 6,186. You'll notice I've put that as a positive value because we're breaking bonds. Breaking bonds is endothermic, and endothermic energy changes are positive. If I now do the same with the other side and bonds forming is an exothermic process. They are negative, so I'm changing the sign on these. 2N triple bond N is 2 times negative 945. 12 OHs is 12 times negative 464, taking us to negative 7458. Now for the final section of this, I'm going to actually put in an energy profile diagram so we can see how we get to the final answer. I've got my positive value going from the reactants up to that point when all of the bonds are broken, and I've put my negative value in down to the reactants. My overall energy change is therefore the overall sum. So I'm going to add together the 6186 and the negative 7458, taking me to a value of negative 1272. Going to move on to Part F, explain why the reaction between ammonia and oxygen is exothermic. Well, in a sense, that energy profile diagram has just given us the answer. What we need to say for this one is that there is more energy released when we make new bonds in the products than was needed to break the bonds in the reactants. Because of those two facts, the net change is that energy was released to the surroundings. And moving on to part G, we have got here 2 marks. We are adding the activation energy and the overall energy change. Now I've added those straight on. You'll notice that my lines both start from the height of the energy that the reactants hold. Not close to the height, they are level with. And my activation energy is very clearly going up to the top of the peak, and your arrow must very clearly reflect that. Your energy change, your overall energy change, must go down to a point level with the energy of the products. That takes us to the end of this question. Thank you for listening.